Welcome. Today's notes worksheet is entitled Right Triangle Trigonometry Day 2, and it's obviously just a continuation of the previous notes worksheet. So actually in this case you're going to need a ruler and a protractor and a calculator for sure there. And we'll just again work on some more things. We're going to look at some of the special angles, of course, and maybe talk about its connection to the unit circle. Certainly just some good right triangle trig coming our way today, and then certainly into tomorrow. And it looks like I also have a fourth notes worksheet with this. So, all right, let's take a look. At the top of the page should just have something that says review of degrees in radians. Obviously, you should know that pi over 6 radians is the same as 30 degrees. Pi over 4 radians is the same as 45 degrees. Pi over 3 radians is the same as 60 degrees. And so what we're going to do is take a look here today at some 45, 45, 90 triangles, see some of the trig ratios formed for that, and 30, 60 right triangles, and see our trig ratios formed for that. I was going to have us do a construction here relating this particular idea. I think I'm going to shortchange it quite a bit if that's all right with you, and then we can focus our attention on some other things. So it says, you know, construction 1, pi over 6 radians is the same as 30 degrees, and kind of why that is just as a review. Well, here's what I'm going to ask you to do. We'll sketch this out rather than constructing it, just to kind of be done with it. But if you don't mind, just go ahead and draw an initial side if you would. And what I was going to have you do is very simply, you were going to measure out 30 degrees. And so I'm going to ask you to just sort of highlight this, and we'll just call it 30 degrees just for our purposes here. So that would be a 30-degree angle right in there that you would have constructed. And then basically what I was going to have you do is grab a compass, and I don't expect you to have one, so don't worry about it. But I was going to have you get a compass and put the compass point here and pencil here, and you were going to sort of come out with a nice circle like this. And as a matter of fact, if you can go ahead and just sketch out a circle just like that, that would be great. And remember how we calculate the radian measurement of an angle. We take the arc length of a circle and divide it by the radius. And so if this truly is 30 degrees, my hope was that you would see that if you were to take your S value, you were going to measure your S value. And so just write this on your paper, and then we can move forward with it. But if you were going to take your S value and divide it by your R value, that would give you theta in radians. That would give you this central angle right in here in radians. Well, if that's 30 degrees, what you would find, everybody, is that the S over R, and again, no matter how big your circle is, S over R would be exactly pi divided by 6. And what you would find, of course, and I've done this in the past, well, pi over 6 is about 0.524 radians, give or take, somewhere in there. But that's what we would see, is if you were to take the S value and divide by the R value, you would always come out with that decimal. You would come out with what is pi divided by 6. And so just, you know, kind of rehashing this idea, 30 degrees is exactly pi over 6 radians. Okay? So again, was going to have you kind of do that piece, but I think we can kind of move forward with it. As long as you understand how that radian measurement is formed and how that would relate to its corresponding degree equivalent there, that would be great. Okay, well, let's go ahead and take a look at the two special right triangles that we're going to see. In this case, you do need a ruler and protractor, so please have one handy. And I know you've seen this before, but it's important for us now to relate sort of the relationships in the sides of these special right triangles to the trigonometric ratios. So that's exactly what we're going to do. So let's do this, everybody. Give me just a horizontal line segment kind of like that. That should do. Grab it with your ruler, of course. And it's up to you how you want to pull this off. But I guess I'll ask you to, from the right-hand side, well, actually, you know what, let's do it from the left-hand side. From the left-hand side, please put your protractor right there and mark off exactly 45 degrees. And I didn't do a great job on that, so I'm going to try to make amends. 45 degrees, and then just kind of have it go out there if you would. And then, when you get an opportunity, please go ahead and, from the right endpoint, can you please mark off 90 degrees? So again, 45 degrees from the left, 90 degrees from the right, and then just something like this would do if you get an opportunity. And should get something along these lines right here. Now, I did not do this justice, but yours is hopefully looking quite a bit better than mine. So that's 90 degrees right in there. That's what you measured with your protractor. That's 45 degrees right in there. That's exactly what you measured with your protractor. And so, of course, this is then 45 degrees right in here. Now I have some extra flack that I'm going to get rid of. I'd encourage you to do the same if you have it. But basically, let's get rid of that. And now we have a nice looking 45, 45, 90 right triangle. Well, what I'm going to ask you to do, everybody, is basically measure the three sides. Take a moment and pause the video and just measure the three sides, this one, and this one, and just put it very light on your paper so you can see it, but that it doesn't overwhelm our diagram. So just very lightly, if this is 6 centimeters, then just put a little 6 right here, etc., etc. Just, again, pause the video for a moment, and please measure those three sides, and just lightly put them in next to the three sides. Okay, so here is what I'm curious, is if you constructed yours correctly, is if you would see the relationships of the sides in a 45, 45, 90. And so here's what I'm going to ask us to do. Put a big X right here. So this first leg, we're just going to call it X. And again, remember how trig ratios work, everybody. The size of the triangle is irrelevant. Your triangle may differ from my triangle up here and all the other triangles that are being drawn with this notes worksheet, but this should still come out the same. And so if that's X right there, I guess this one's a fairly easy one. I'm hoping everybody saw that this was the exact same number of units as this right here. So whatever this is the same. So if that's X right there. And I hope you saw that. If you didn't see that piece, then maybe you have to go back and measure that angle again. But you should see those two sides are the same. Now, if you don't mind, try to think back to your geometry class a little bit. And does anyone happen to remember how to go from the leg in a 45, 45, 90 to the hypotenuse of the 45, 45, 90? The hypotenuse is obviously bigger. So just to give you a hint, we actually multiply by a particular constant. Anyone happen to remember what we multiply it by? Okay, here's the moment of truth. Whatever this length is right here, if you multiply it by square root of 2, it should be equal to the hypotenuse. So if this is x times square root of 2. And so what I'm going to ask you to do is just see how you did on this and confirm it. But basically, you have the length right here that you calculated. If you can go ahead and take that number on your calculator and multiply it by square root of 2, and that should be the length of your hypotenuse. If you've done your construction perfectly, that would be the case. And that's our relationship right there. Regardless of the three sides, that is the side relationship in a 45, 45, 90. Okay, now what that allows us to do is start talking about the trig ratios. And so let's go ahead and take a peek. Now we could go for either 45-degree angle, but I'm going to go ahead and just use this one. It's a little better visually for me. And basically what I'm going to ask us to do is take the sine of 45 degrees. Well, everyone, that would be the opposite over the hypotenuse. So again, just really rehashing some ideas from the previous notes worksheet, opposite over hypotenuse. Now here's the beautiful thing about this, everyone. It doesn't matter what the lengths of your sides were. That's the relationship. And so what would happen to the x's? They should cancel. So those get slashed, and you end up getting 1 over square root of 2, and which would be square root of 2 over 2. Now, everyone, think back. Here's where that comes into play. Think back to the unit circle, of course, please. And if I asked you for the sine of pi over 4, what would you tell me? Square root of 2 over 2, of course. And this is where those numbers come from. If you remember, I kind of gave you those numbers on the unit circle, and I said, well, you'll have to take my word for it. I'm hoping you see that they should be the decimal approximations. You could see that at pi over 4, the y coordinate was about 0.707, which is root 2 over 2. But you kind of took my word for it that it was exactly root 2 over 2. And here's where you can see it. Sine of 45 degrees is root 2 over 2. The sine of pi over 4 radians, of course, because it's the same angle, is root 2 over 2. Excellent. Well, let's kind of just continue a little bit here. I'll focus mostly on the primary 3, and then we'll just fill in the secondary 3. Cosine of 45 degrees, again, would just be adjacent over hypotenuse. Same deal. And this should come as no shocker. So you get the 1 over root 2, and the sine of pi over 4 and the cosine of pi over 4 are the same, both root 2 over 2. And you can really see these numbers unfold in this context. I like it. Tangent of 45 degrees, everybody. Opposite over adjacent. X over x. Remember, the size of the triangle is irrelevant, as we saw in the last piece. It's the ratios that matter, and no matter what, in this particular case, if you were to take the opposite over the adjacent, you're going to get 1. Tangent of pi over 4 is 1. Wonderful. Just if you happen to reduce or sort of flip all of those, you get root 2, you get root 2, and you get 1. Again, you should be able to kind of do hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. But for those three, we're just going to go ahead and shortchange it a little bit. Okay, so 45, 45, 90s. It's just another way to really remember those. If you know your unit circle, which you should, then this is just another piece to help reinforce it. And definitely not reinventing the wheel with this, just giving you a different representation of our same results. Okay, a couple ways to construct this one, so I'll ask you to do what works for you here. I think I'm going to do it this way, at least initially. So give me a horizontal line segment, kind of like that, if you would. And what I'm going to ask you to do, guys, is now go 30 degrees from the left and 90 degrees from the right. So what I mean by that, of course, is come on over here, measure 30 degrees from that left vertex, and then come over here and do 90 degrees from the right vertex, and should be getting something like this. So 30 degrees and then 90 degrees right there. So please take a moment and construct this out. I'm going to ask you to construct and measure and do all that fun stuff right in there. And so that's going to be 30 degrees, that's going to be 90 degrees, and that's going to be 60 degrees right in there. Again, if you fall behind at all, please pause the video at any time. Should have a triangle that looks something like that, give or take. Okay, and again, it's just a good visual representation, good way to see some of these in action. I'm going to ask you to take a moment, please, pause the video, and measure the three sides in your triangle here. And just very lightly put those numbers by each of the three sides. So measure the three sides and put those numbers in play. Okay. Well, in this particular case, let's start from the small side, if you would. And so we're going to call that Y. So that would be the smallest leg in the 30, 60, 90. And let's see if you remember your relationships here. So the easiest one to see is the relationship between the small leg and the hypotenuse. And if you look at your numbers, you would see that to get from the small leg to the hypotenuse, you should double it. And so you can do just a quick check on your numbers, see if you did it properly. But if you go ahead and take your small leg and multiply it by 2, that should be your hypotenuse length. That's the relationship in the 30, 60, 90. And then also, to go from the smaller leg to the longer leg, we also multiply it by a constant. And if you remember correctly, just to keep this moving along for you, we would multiply it by square root of 3. So whatever this number is right here, if you multiply it by square root of 3, it should be this number right there. And you can go ahead and check. Pause the video for a sec and multiply your small leg by root 3 and see if that is equal to your long leg. Okay, what that allows us to do, everybody, is really start to see some of these unfold. Let's go with the 30s there, and then maybe we'll go with the 60s too, see some good things in action. So if I asked you for the sine of 30 degrees now, based on those relationships, we should be able to pull it off. And again, if you know the sine of pi over 6, then this should be perfectly clear. Well, again, guys, 30 degrees. Here's 30 degrees right here. Opposite, hypotenuse. Opposite over hypotenuse is y over 2y, and you could see those would cancel, and the sine of 30 degrees is exactly 1/2. The sine of pi over 6 is 1/2. This is one that you're going to see nicely fit in with the unit circle as well. Cosine of 30 degrees. So everyone here's 30 degrees, adjacent, hypotenuse, and so you get y root 3 over 2y. The y's cancel. And remember, kind of looked at this on the unit circle. we saw it as about 0.866, and I'm hoping you saw that visually, but now you can really see where that root 3 over 2 number comes from. So cosine of 30 degrees is root 3 over 2, just like on the unit circle, everybody. Cosine of pi over 6 is root 3 over 2. Okay, let's see tangent, 30 degrees. So that would be opposite over adjacent. So that would be y over y root 3. And we get 1 over root 3, which means we get root 3 over 3. So do you remember the way we kind of remembered this? We did it in radians. And if you remember tangent of pi over 6, 3 plus 3 is 6. So that's how you know the root 3 over 3 goes with that particular angle, the pi over 6. So some way, shape, or form, you're going to have to know that piece. Tangent of 30 degrees is root 3 over 3. Okay, let's just go ahead and round these out then. So this would be 2y over y, which is just 2. And again, you kind of flip these around, do the reciprocals. You would get that, and you would get that, and you would get that. Again, I don't do too much with those reciprocal ones. Understanding the primary 3, sine, cosine, and tangent, allows you to get the other ones pretty quickly. Okay. Now we're going to do the 60 degree. Now you don't have to do this on your paper, but sometimes it's good visually to kind of see it. So you can just kind of take a look up here. There was another way to draw the 30-60 coming 60 degrees from there, and that would make this 30 degrees up there, which would be, this would be the y, this would be the y root 3, and this would be the 2y. I kind of like this perspective when you think about the 60s. This is how I certainly envision it in the right triangle context. And so, again, the relationship still holds, so you can kind of look at it here. Opposite is the longer side there, so 60 degrees produces that longer side, not y, but y root 3 over the hypotenuse. And so you could see in either one, of course, you get y root 3 over 2y, and so sine of 60 degrees, everybody. We all know it as root 3 over 2. Cosine of 60, and again, I sort of envision it with such a steep angle, it has a small horizontal with the hypotenuse there. So the small horizontal is the y, and the hypotenuse is the 2y. So again, so many just different ways to perceive them and to look at them. But basically, you have to know cosine of 60 degrees is 1/2. Tangent of 60, and again, you've got a steeper, in this case, opposite side in relation to a shorter adjacent side. So this in this particular case, you get y root 3 over y, and so tangent of 60 degrees is root 3. The way we did it in radians was tangent of pi over 3, so the pi over 3 is just the root 3. Again, those work really nicely. I'm going to go ahead and just flip. So cosecant of 60 would be this, secant of 60 would be this, and then cotangent of 60 would be this. Good. One connection quickly to make here, and then we'll start to work on the back side a little bit. So basically, just don't forget one thing we did on the previous notes worksheet, cofunctions complementaries. That works pretty nicely right here. And so here's what I'll ask you to do. Just look. Don't write anything down. But what if I asked you for the sine of 60? I'm sorry, sine of 30, right up there, sine of 30 degrees. Using the concept of cofunctions and complementaries, the sine of 30 should be the same as the cofunction, which is cosine of its complement. So take a look. Sine of 30 is 1/2. Cosine of 60, 1/2, of course. Because remember, it relates the same two sides. Let's just do one more here. How about secant of 30 degrees? What should that be the same as? Secant of 30 should be the same as cosecant of 60. Cofunctions, complementary angles are the same. So again, it just works nicely on those 30, 60, 90s there. Okay, let's take a look at the next piece. So it's one thing, of course, to just memorize these values, and that is definitely a part of it, although I wouldn't call it memorization. I would call it visualization. But it's also going beyond just those special values there and really understanding the behavior of sine, the behavior of cosine, and the behavior of tangent on these intervals, because that's going to really allow us to take the next step and the next step after that. So I guess here's what I would ask you. think about it for a sec, and then let's kind of fill these pieces in. Do the sine values increase or decrease on the interval of 0 to 90 degrees? So I'm just going to put a couple of right triangles here. I'm going to put one with a small theta, and then maybe one with a large theta, kind of helping us out there. So I don't know if that is helpful or not, but it gives you a sense of, okay, well, if theta is small, think about what would happen with the opposite over hypotenuse. Think about that. Whereas if theta is larger, what do you think about the opposite over hypotenuse? And so what do you think here? Do the sine values increase or decrease as theta gets larger and larger and larger? As theta goes from here, up, 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 what happens to the opposite over hypotenuse? And if you can really visualize it, I think you would see that the sine values increase on that interval from 0 to 90. Now, if sine increases, well, let's see what happens with cosine. So as theta gets larger and larger and larger, let's look at the adjacent side to the hypotenuse. And think about this. Here's the adjacent. Here's the hypotenuse. Then here's the adjacent. Here's the hypotenuse, a little longer. I'm hoping everybody would see that initially the adjacent over hypotenuse is fairly large, and as theta gets bigger, that adjacent side is going to get smaller and smaller and smaller in relation to the hypotenuse. So I'm hoping you all see that the cosine values decrease. And then how about tangent? Last one here. Again, really see the behavior. Think more dynamically as opposed to statically. Okay, and how about tangent then? Increase or decrease? Opposite, adjacent. Look at it initially. Look at it after as theta increases and increases and increases. And I'm hoping you would see that really the opposite in relation to the adjacent is just going to get larger and larger and larger there. Good. So what we're going to do here is just fill in this table, use a little of the unit circle to help us out, and use this piece right here. And you can really see this in action. So the sine of 0, everybody, if you remember from the unit circle, is 0. Sine of 30 degrees is 1/2, which I'm going to go ahead and put just as the decimal approximation. Sine of 45 degrees is √2/2, which again is about 0.707. Sine of 60 degrees is √3/2, which is about 0.866. Again, you can see it getting larger and larger and larger. Now think about unit circle. What's the sine of pi/2? Or what's the sine of 90 degrees? And it should be 1. So you could see what happens here. Sine increases from 0, going up, going up, going up, to 1. Good. Should fit perfectly in. It's great. Cosine of 0, if you think back to the unit circle, cosine of 0 actually is 1. And then now use some of the ideas from the front side. Well, cosine of 30 degrees is √3/2, again about 0.866. Cosine of 45 degrees is √2/2, about 0.707. Cosine of 60 degrees is 1/2. And when you get up to the top of the unit circle, the cosine of 90 degrees, or the cosine of pi/2 radians, is definitely 0. So you can see cosine decreases on that interval. It's going down, down, down from 1 all the way down to 0. Excellent. How about tangent? Tangent's an interesting one. Its behavior. Tangent of 0 is 0. Tangent of 30 degrees is that √3/3. Let's get a decimal on that. Just kind of thinking about that piece right there. Let's do square root. You don't have to do this on yours. I'll just do it quickly up here. Square root of 3/3. So about 0.577, give or take. And then tangent of 45 degrees is 1. And then what happens to the opposite side in relation to the adjacent side after 45 degrees? Well, the opposite side is bigger, so it's going above 1. By the time we hit 60 degrees, it's √3, which is about 1.73 something there. And then it's going to get larger and larger and larger. What happens at 90 degrees, everyone? What is the tangent of pi/2? Well, the tangent of pi/2 happens to be undefined. So what does that mean for us, essentially, is that the tangent values, as you can see, are getting larger and larger and larger. they're going to get infinitely large as we get closer and closer to 90 degrees. And you could try this on the calculator. If you're in degree mode, type in tangent of 89, tangent of 89.9, tangent of 89.99, et cetera, et cetera. And as we get closer and closer to 90, the tangent values really shoot higher and higher. Excellent. Okay, again, hoping you're really starting to understand not just the particular values, but the behavior of those values. Okay, it's time to get into some of the problem solving with the right triangle trig here. So I'm going to ask you to do one more construction with me and really kind of see this in play, and then we'll go from there. Okay, so here's what I'm going to ask you to do. Use your ruler, please, and come up with a horizontal line segment. And then I guess what I'm going to ask you to do is just go ahead from your right endpoint, mark off 90 degrees. So grab your protractor, and please mark off 90 degrees from the right endpoint. And then, I don't care, it makes no difference. Just use your ruler to go up through that point and go up a certain amount. And then you can just go ahead and now make your right triangle kind of like this, and that should be fine. Now everyone, our standard right triangle, the one you're going to use really in all the problem solving on the homework and the take-home quizzes and so forth, will be little a, little b, and little c. So those are the three sides, A, B, and C, which are going to correspond to three angles, by the way. And the angles will be across. So if little a is over here, guys, then big A is going to be right here. So if you get an opportunity, that's big A, big B, so angle B right up there, and then angle C will be our right angle there. And that's what it's going to look like, everyone. And what I'm going to ask us to do is actually measure, as it says, one side and one angle. You're going to measure those two pieces. And the idea being, using math, and specifically trigonometry, if we're given just one side and one angle in this right triangle, we should be able to calculate the rest. So here's what I'm going to ask you to do. Let's do, well, let's measure angle A first. So measure angle A if you would. And I'm going to measure my angle A. I'm going to actually grab a protractor and, to the best of my ability, just kind of measure this piece. And I get about 25 degrees. So I'm going to use that number right in there. It might not be perfect, but it's as good as I'm going to get with this. And then what I'm going to ask us to do is now measure one of the sides. So you've measured that angle right in there, angle A. That's the one angle. Now what we're going to do is pick any one of the three sides. It really doesn't matter which one we pick. I'm going to ask you to just do side B. And so in this particular case, everyone grab the ruler, please, and measure from here to here. I'm going to put in a number so I can use. As we go through the process, you're going to use your number, though. Okay? All right, so everyone, please measure side B. And I'm going to put in my number right there, and we'll go with exactly 10. Okay, now here's the premise behind it, is that we should be able to find the remaining three pieces in this right triangle. We have the right angle, of course. I asked you to measure angle A, and I asked you to measure side B. We should now be able to get the other angle, and now the other two sides as well. Okay, so you're going to be using your numbers, I'm going to be using my numbers, and hopefully it'll make pretty decent sense. So guys, down on your paper here it says strategies for solving a right triangle when given one side and one angle. It's a three-step process for the three pieces we need. So I guess the first order of business is to actually find the secondary angle, or really the last angle here, as we already have the right angle. So I guess here's what I would say. The second acute angle is the complement, of course, of the first acute angle. So guys, we're in degree mode, of course. And so in this particular case, I would say that this is 65 degrees for me. So I would just do a 90 minus, end of story. Now I'm just kind of thinking about your diagram here. If you get an opportunity, it's not that big of a deal, but just kind of distinguish between what was given and what we solved. Just maybe very lightly on your paper, circle the two things that were given. So I'm going to circle my 25 degrees and I'm going to circle my 10. So those are the pieces that were given. I'm just kind of thinking, so we know that, when you look back on this, we solved for the 65. It was not given. Okay, so that's the easy one. I always do the easy part first. And so number one, done. Found the other angle. Now there are only two pieces left, and it happens to be number 2 is the big one here. So we're going to, actually this is the only step that requires it, but we are going to use a trig equation to find, really to solve for the second side. So as we go through the process here, this is the only one that requires any trigonometry. Now again, let me be very clear. Please use your numbers, not mine. I'm just going to obviously set up what I have here. And we have a choice, of course. We can do either little a or little c. Just because I'm working through this particular piece by myself at the board here, I'm going to ask us to solve for little c. Okay, so we're going to solve for little c. So forget A for just a minute. That will come last. So what I want us to do, everybody, is focus on the angle that was given, in this case, big A, the side that you measured, in this case, little b, and then the side that we need. And so here's the idea. I'm going to go ahead and just put my angle right here for just a moment. And basically, remember, every angle in a right triangle has 6 ratios that go with it. We only need one of the primary 3, either sine, cosine, and tangent. We just have to decide which one it is. So now let's go over it one more time. I have the adjacent side, and I want the hypotenuse. So as soon as I talk about those two sides, the adjacent and the hypotenuse, which ratio in reference to theta am I talking about? And it has to be cosine. So the cosine ratio of our angle is equivalent to the adjacent side, which you solved for, you measured, and the hypotenuse, which is what we're trying to solve for. So again, let's just go over that one more time. Cosine ratio, because have the adjacent, need the hypotenuse. Adjacent and hypotenuse is cosine. So what you're going to do is, at this stage, again with your numbers, you're going to actually calculate the cosine ratio of your angle. So I'm going to move this over here. And one thing, just be very clear, degree mode on your calculator. And so I'm going to type in cosine of my angle, which was 25 degrees. That is stored in there. And what it's basically saying is the adjacent over the hypotenuse for a 25-degree angle is always the same number. And I'm going to go ahead and write that in there, about 0.9063 for me. And that equals my little b over c. So again, that number is stored in the calculator. Again, typically we go to about 4 decimal places. What I like to do, everyone, is just put it over 1 and cross multiply. But if you know some shortcuts and you can work this out, then please feel free to do exactly that. So now that we have that as a constant, I cross multiply and I get 0.9063c equals 10 times 1. And so c is equal to 10 divided by 0.9063. So for me, everybody, I took my little b and I divided by the cosine of my angle. I'm going to go ahead and do that just to make sure we have everything squared away there. And so for me, 10 divided by 0.9063 is equal to that right there. And again, we're not going to go 4 decimal places on this, so about 11, just over 11. And that would be the length of the hypotenuse. Now, there's only one way to figure out if you did yours correctly. Measure your hypotenuse. So if you set up a trig equation and solved for little c, it should be equal to that measurement. So literally, grab the ruler, please. Measure from here to here. For me, it is exactly 11.03. Absolutely perfect. Okay. Now just the last piece of the puzzle here. I have 2 sides, and I need the third. You can use trig, but there's no need here. I think there's something easier. Anytime we're talking about a right triangle given two sides and trying to find the third, I would just say use the Pythagorean theorem to get the third side. And again, when you get an opportunity there, please do it and then measure. Make sure it worked. So for me, it would be 11.03 squared minus 10 squared equals a squared. Dot, dot, dot. I'm not going to do the calculation there. I think you can kind of work that out yourself and then figure out what a is. And then come up with that measurement and put that in right there if you get an opportunity. Whatever that is, put it in. And that's basically it. That's how we're going to solve these right triangles here. The key, of course, is number 2, working through an equation there. Okay. Well, I hope it worked out with your construction. If it didn't, let me know, and I'll be happy to help you. What I'm going to ask you to do is to try this one out. Pause the video and solve the right triangle. And then if you can come on back there, and I'll give you some answers, or I'll solve it. In fact, I don't think I have this one on my sheet, so I'll have to solve it too, and then we'll go from there. So it looks like you're going to need little a, you're going to need little b, and you're going to need big B. So everyone, again, pause the video for a moment, and then check back in after you've completed example 2. All right, well, let's see what we have going on here. So first order of business is to get the big angle B. So I hope everyone did this nicely here, just 90 minus 29.5, and that works out great. Should get 60.5 degrees. So first one there, 60.5 degrees. Now it's up to you which one you want to solve for first. I'm just going to go alphabetical. It's just the way I see it. So I'm going to go ahead and get little a first, so from here to here. And basically, here's the concept then. With that 29.5 degrees, that's the one I'm going to use. I need the opposite side, and I have the hypotenuse. Opposite, hypotenuse. That's the sine ratio. So the sine of 29.5 is equal to a over 12.2. I'm going to get the sine of 29.5 degrees, and I'm hoping you'll see that when we cross multiply, all I really need to do is multiply that by 12.2. So if it's okay with you, I'm going to go ahead and do exactly that. Let's get that one more time. And let me move this back over so we can get that squared away. So sine of, where is it, 29.5. I'll get that first for you. First would help if I had it on. So sine 29.5. Good, and that looks great. And by the way, remember, sine of 30, everybody, is 0.5. Sine of 30 degrees is exactly 1/2. And notice, just below 1/2. And then I'm going to take that answer and multiply it by 12.2. And so you should see it's just over 6. So since it was this type of decimal, I'll go ahead and do it that way. And then, guys, of course, just a little Pythagorean theorem here. So we've got the 60.5 right here. I have the 6.007 right there. And again, the only reason I went out 3 decimal places is just so you would know it's not exactly 6, but it really doesn't matter a whole lot. 1 or 2 decimal places is more than adequate on these sides. And then let's go ahead and just do Pythagorean theorem on this. Hypotenuse squared minus the 1 leg squared equals that 3rd leg squared. And I'll do this calculation, just make sure you have it. I'm sure this worked out just fine for you, and if not, you'll let me know. So just this piece right here. And then let's square root that answer. So about 10.62, give or take. And that is it. Okay, looking great. So I hope you worked through this one. It's just a good problem to see if you're on the right track with this. If you have any questions at all as you went through some of the constructions and all that, please don't hesitate to ask. There's obviously some great problem solving with some right triangle trig. But I like that we're now starting to talk about not just the values, but the behavior of sine and cosine and tangent as that angle changes, as that number changes. So perfect. If you have questions, let me know. And as always, everyone, I appreciate you listening, and I hope the lesson worked for you.